The float charge voltage per cell is slightly higher than the open circuit cell voltage. A typical float charge voltage is 2.2 volts per cell. So the in-service cell voltage for this battery, measured across the terminals of one cell, should be 2.2 volts. And the in-service battery voltage should be 2.2 volts times 24 cells, or 52.8 volts. Now, in-service cell voltage is one indication of a battery's state of charge. In our example, an in-service cell at full charge should provide about 2.2 volts. As the cell discharges, the voltage decreases. When a cell is almost completely discharged, its voltage falls off rapidly to a value called its final voltage. The final voltage of a lead-acid cell is about 1.7 volts. The closer the cell voltages are to full charge, the more likely it is that the battery will be able to provide backup power when it's needed. A better indication of a battery's ability to provide backup power is its capacity. Battery capacity and cell capacity are the same. Capacity may be tested, but on a less frequent basis than voltage testing. The capacity of a cell is defined by its ability to supply a constant current for a specified number of hours. Cell capacity is typically rated in ampere hours. For example, a cell that's rated at 1 ampere hour when fully charged would be able to supply a current of 1 amp for 1 hour before fully discharging to 1.7 volts. Manufacturers typically rate cells based on an 8-hour rate of discharge. For example, this cell is rated at 200 ampere hours. This means it should be able to supply 25 amps of current per hour continuously for 8 hours for a total of 200 ampere hours. The capacity of a cell changes with different current demands. For example, if the load demands 35.2 amps from this cell, the cell will be able to provide 35.2 amps for only 5 hours. This translates into an ampere-hour rating of 176. So the cell capacity, or ampere-hour rating, is lower at higher discharge currents. On the other hand, if the load demands 20 amps, the cell can provide this current for 12 hours. This represents an ampere-hour rating of 240. So the cell capacity is higher at lower discharge currents. Another indication of a battery's state of charge is the specific gravity of the cells. The specific gravity of a cell is defined as the density of the cell's electrolyte in relation to the density of water. The electrolyte in a cell is composed of sulfuric acid and water. As a cell is discharged, sulfuric acid leaves the electrolyte and combines with the lead in the plates, decreasing the concentration of sulfuric acid in the electrolyte. So a test that reflects the concentration of sulfuric acid in the electrolyte will show the state of charge of that cell. That test is for the specific gravity of the electrolyte. The specific gravity of the electrolyte is the density of the sulfuric acid in relation to the density of the water in electrolyte. For example, 1 pint of water weighs about 1 pound. The weight of 1 pint of sulfuric acid is a little more than 1.8 pounds. When specific gravities of liquids are computed, a value of 1 is given to water. The specific gravity of sulfuric acid is 1.839. Any mixture of water and sulfuric acid, then, would have a specific gravity between 1 and 1.839. The specific gravity in a fully charged cell is typically around 1.210. As the cell discharges, the specific gravity of the electrolyte decreases because sulfuric acid leaves the electrolyte and combines with the lead in the plates of the cell. When the cell is recharged, the specific gravity increases because sulfuric acid is driven off the plates and back into the electrolyte. So the specific gravity of a cell provides another indication of a battery's state of charge and its ability to provide the required backup power when it's needed. In-service cell voltage, capacity, and specific gravity are all indicators of a battery's state of charge and its ability to provide backup power. and the value of each of these indicators is related to the value of the other two indicators. The relationship of voltage, capacity, and specific gravity can be shown using a simplified chart. The vertical axis represents values of cell ampere hours, cell specific gravity, and cell voltage. The horizontal axis represents time. The time is divided into discharge time and charge time. Separate lines are used to indicate changing cell ampere hours, cell specific gravity, and cell voltage. When a fully charged cell discharges, cell voltage drops gradually. Then, when the cell is almost completely discharged, the voltage falls off rapidly to its final voltage. At the same time, the cell's ampere hours of capacity decreases at a constant rate, and the cell's specific gravity decreases at the same rate as the ampere hours. When the cell is discharging, its voltage and especially its specific gravity change at a relatively constant rate. So, a measurement of either cell voltage or specific gravity during discharge will give a fairly reliable indication of how many ampere hours of capacity are remaining in the cell. However, when the cell is recharging, cell voltage and specific gravity change at irregular rates. Cell voltage jumps instantly and then gradually increases till it matches the output voltage of the battery charger. Cell-specific gravity increases gradually as sulfuric acid is driven off the cell plates and mixed with the electrolyte. It may take weeks or even months for the sulfuric acid to thoroughly mix with the electrolyte and for the specific gravity to return to its normal value. Because cell voltage and specific gravity change at irregular rates when the cell is recharging, they are not reliable indicators of cell ampere hour capacity when the cell is recharging. Better indications are the voltage and current meter readings on the battery charger.